Hello all, welcome to Marri Laxman Reddy Institute of Technology and Management. So this is S. Kumar working as an assistant professor for the Department of Electrical and Electronics Engineering. So today I am going to explain about the topic called dot convention in network analysis and synthesis. This comes under the module 1 for the first year second semester ECE students. So this is the topic today I am going to explain, that is dot convention. So first of all, in previous lectures I explained about self-inductance and mutual inductance of a coupled magnetically coupled circuits. So this is the basic concept called dot convention. It is used to determine the relative polarity of a induced voltage in a coupled circuits, in a magnetically coupled circuit. So here the dot convention. Why the dot convention is used? The dot convention is used to determine the induced voltage in a coupled circuits. So this is the primary use of a dot convention in magnetically coupled circuit to determine the polarity, in particularly the polarity of induced voltage. So that is the main use of dot convention. This is the concept called dot convention. It is used to determine the relative polarity of a induced voltage. The polarity, in simply we can say that the polarity of a induced voltage in magnetically coupled circuit. So in previous classes, so what is the magnetically coupled circuits and what is the mutual induced voltage and self induced voltage we have seen. So here how the dots are marked in a magnetically coupled circuits. So here, so we know that the mutual inductance, so we are representing with a capital M. So this is a mutual inductance. So this mutual inductance is always positive quantity. So in a magnetically coupled circuit, the mutual inductance is a positive quantity. Always it is a positive quantity. So, but whereas the mutual induced voltage, M, that is given by M di by dt. So M into di by dt is the mutual voltage, that is mutual induced voltage in a magnetically coupled circuits. So this mutual voltage M di by dt, it may be a negative value or it may be a positive value. So that can be decided by the dots on each and every coil of a coupled coils. So here dots are used along with the dot convention to determine the polarity of this mutual voltage. So as I said, the mutual voltage or induced voltage. Here the mutual induced voltage. So this one. So M into di by dt is the mutual voltage in a magnetically coupled circuits. So to determine the polarity of this mutual voltage M di by dt, so dots are used. So here I am considering two different circuits. Here this is one circuit A and circuit B. Here I am considering a coil 1 of inductance L1 and coil 2 of inductance L2. So here I am taking a current I1 is entering at a dotted terminal of coil 1, and similarly, so this is the dot in a second coil is a positive terminal. So here the mutual voltage that is given by M di1 by dt. So this is a mutual voltage in this circuit due to current I1 in coil 1. So this is a mutual voltage. So mutual voltage is positive when the current I1 is entering at a dotted terminal of first coil and the dot is present at positive terminal of second coil. So this is one case. In this case, the mutual voltage. So that is mutual voltage M di1 by dt is the positive. In consider a second coil, second circuit here. So here the current is entering at a dotted terminal in first coil, and whereas the dot is present here. Dot is present in the second coil at negative terminal. So in this case, the mutual voltage, so that is V2 is equals minus di1 by dt. So this is a mutual voltage when current is entering in first coil, dotted terminal of first coil, and whereas the dot is present at a negative terminal of a second coil. In this case, the term M is negative. The mutual voltage is negative of M into di1 by dt. So this is a second case. So here the different combinations. Here the combination of a coupled circuit here is current I1 is entering at a dotted terminal of first coil. In second circuit also the current I1 is entering at a dotted terminal of first coil. But in this first circuit, the dot is present in a second coil at positive terminal. If it is at positive terminal, the mutual voltage is positive. So in the dot at second coil at negative terminal, the mutual voltage is negative. So this is need to be remembered. So in second case. So here I am considering current is leaving from dotted terminal of a one coil. So here you can see, you consider say first circuit, this is circuit C and circuit D. In both the circuit, the current is leaving from the dotted terminal of a first coil. Here I1 is leaving from dotted terminal of a first coil. So this is the coil 1. Here dot is mentioned here. So from this one, the I1 is leaving. The current I1 is leaving. Here in this circuit also, the current I1 is leaving. Current I1 is leaving from the dotted terminal of a first coil. In both the cases, I1 is leaving from the dotted terminal. You can observe here. So in the second coil, the dot is present. Dot is present at positive terminal. If it is present, if dot in the second coil present at positive terminal, the mutual voltage is negative. Similarly, if dot is present at a negative terminal, dot is present in second coil at a negative terminal. If it is present at a negative terminal, the mutual voltage is positive. So this is the case. When here this is the case, I1 in first coil. I1 is leaving from dotted terminal in first coil. So this is the case. I1 is the current in a coil 1. So this current is leaving from dotted terminal of first coil. So if it leaves, so in the second coil, the dotted terminal, if it is at positive terminal, the mutual voltage is negative. Mutual voltage is negative. So the dot is present at negative terminal. So then the mutual voltage is positive. It is negative it is positive. If it is negative terminal, dot is present at negative terminal, the mutual voltage is positive. Reverse. If dot is present at positive terminal, the mutual voltage is negative. So this is the case. Whereas if dot is entering, the current is entering at a dotted terminal of a first coil. So here, if dot is present, so you can see in first case, what do we have observed here? Here, here I1 is entering at a dotted terminal of first coil. So I1 is entering at a dotted terminal. If it is entering, so if dot at second coil at positive terminal, if it is at positive terminal, the mutual voltage is also positive. So the dot in the second coil at a negative terminal, if it is negative terminal, the mutual voltage is also negative. When the current I1 is entering at a dotted terminal of a first coil. In the second coil, the dot is at positive terminal, mutual voltage is also positive. If dot is at negative terminal, the mutual voltage is also negative. If current is entering at a dotted terminal of a first coil. So in a second case, here it is different. If current I1 in first coil leaving from the dotted terminal, if it is leaving, it leaves dotted terminal of a first coil. So the dot at second coil, if it is at positive terminal, the mutual voltage is negative. Reverse to this one. So if it is, the dot is at negative terminal of second coil, the mutual voltage is positive. So this is the case. In this way, we are determining the mutual voltage, the polarity of a mutual voltage. So this is a mutual voltage. In second coil, this is a mutual voltage. So in this way, we are determining the polarity of a mutual voltage by marking a dots on each and every coil of a magnetically coupled coils. So this is all about. So this is all about dot convention. Here we are considering in that way. So here analyzing the circuits. So next one is we are analyzing the circuit involving mutual inductance. So if we are considering, here we are considering two coils, coil 1 of inductance L1, coil 2 of inductance L2. The mutual inductance between these two coils is M. Here these two coils are connected in series. So but we need to consider the dots. So here in the first coil, dot is present here, the current is entering in dotted terminal. In second coil also, dot is present at starting, the current is also entering in dotted terminal of second coil. If these two are, the currents are entering at dotted terminals. So then this connection we call it as a series aiding connection of a two different coils. Coil 1 and coil 2 are series aiding when a current is entering at dotted terminal of first coil, and also the current is also entering dotted terminal of a second coil. If it is like that, so that we call it as a series aiding connection of a magnetical coils, two coils. In this case, the mutual inductance, we write it as a 2M. So that is self-inductance or a total inductance of a coil. Series connected coils are L1 plus L2 plus 2 times mutual inductance. So in this second case, so if series opposing connection, what is the meaning of series opposing connection? Here consider two coils L1 of inductance, coil 1 of inductance L1, for coil 2 inductance is L2. Here dot is For first coil, dot is here. For second coil, dot is mentioned here. So if you are observing a current flow, so current is entering a dotted terminal of a first coil, whereas the current is leaving from dotted terminal of a second coil. Here current is entering into the dotted terminal of first coil. Here current is leaving or comes out of dotted terminal of a second coil. In this connection, we call it as a series opposing connection of two coils. In this case, the total inductance of a coupled coils is given by L1 plus L2. Here the mutual inductance is negative, minus 2M. Here for a series opposing connection of a two coils, the total inductance is given by L1 plus L2 minus 2M. M is the mutual inductance, whereas a series aiding connection of a two coils, so the total inductance is given by inductance of coil 1, inductance of coil 2 plus 2 times the mutual inductance between the two coils. M is the mutual inductance between the two coils L1 and L2, coil 1 and coil 2. So this is total inductance of a coupled coils connected in series. So how to represent in time domain? The time domain representation of two coils. So here these are the two coils which are coupled each other. So here for first loop the current I1 is flowing. In second loop current I2 is flowing because of V2, because of V1 I1 is flowing. So while writing, by applying KVL to the first loop or first circuit, so V is equals the drop across resistance R1, I1 into R1. So the inductance, induced voltage, self-induced voltage, L into di1 by dt, and mutual voltage M times di2 by dt. Because here in first circuit I1 is entering at the dotted terminal. In second circuit also current is entering at dotted terminals. In both the cases current is entering at dotted terminals of two circuits. That's why we are considering the term M as a positive. That means that the mutual voltage is positive. Next, I am writing for coil 2. I am applying KVL to the coil 2. Here V2 is equals voltage across coil 2 is equals I2 into R2 plus self-induced voltage, that is L2 di2 by dt. Here also the two currents are entering at a dotted terminal. If current is entering at a two dotted terminals, the term M is positive. Here also plus M I1 by I2. So this is a mutual voltage is because of current in coil 1. This is a mutual voltage due to current in I2. That's why I am writing M di2 by dt. So here I am writing M di1 by dt. So this is a mutual voltage because of current in coil 1. So this is a mutual voltage because of current in I2. Current in circuit 2 or loop 2, I2. So here this is a way to represent the two magnetically coupled coils in time domain. So here the frequency domain representation of a two magnetically coupled circuit. So in frequency domain, here also I am considering dots at this point, at this terminals. So here also current I1 is entering at the dotted terminal. Here also current is leaving from the dotted terminal. In this case, current circuit current I1 entering a dotted terminal, circuit 2 current is also entering a dotted terminal. That's why the mutual voltage is positive. I am considered. So here the current in the circuit 1 is entering a dotted terminal. The current in circuit 2 leaves from the dotted terminal. In that case, if you are applying KVL to the loop 1, so this is the voltage. Voltage is equal, supply voltage is equal, so drop. So Z1 is the impedance, I1 is the drop for across the inductance. So J omega L1 into I1. So this is the inductance and the mutual voltage. Here the mutual voltage is negative because here the circuit 1 current is entering at a dotted terminal, circuit 2 current is leaving from the dotted terminal. That's why, so I am considering the mutual voltage as a negative, but here I am representing this voltage in a frequency domain. In previously, I represented in time domain. This time I am writing the parameters or voltage drops in terms of frequency, that is J omega. J omega is a frequency representation. Similarly, in loop 2, so there is in a circuit 2, in circuit 2 there is no voltage. That's why the apply voltage is 0. So it is equals the drop across Z2 impedance. Sorry, it is ZL, load impedance ZL. I2 into ZL is one drop across the impedance, and J omega L to I2 is a voltage in a coil 2, and this is a mutual voltage minus. I am writing minus sign because the current is leaving compared to current is entering in circuit 1. That's why this is the 1. So in this way, we are representing two magnetically coupled coils in time domain representation and frequency domain representation by considering a dots in a magnetically coupled coils. Next, we will see one problem based on dot convention in a magnetically coupled circuit. So here, for a given circuit, calculate the phasor currents I1 and I2 in the circuit. The circuit is given, so 12 at an angle of 0. Current I1 is I am considering. This is the impedance is given. So this is a mutual impedance, and this is the J 5 omega L1 and L2 J62. So here, just applying like previously, I am considering loop 1, I am applying the KVL for loop 1. So we know that, so this is the drop. So this is the voltage minus 12, and this is the impedance. Impedance is a minus 4J and plus 5J into I1, and this is the mutual impedance. So J is the mutual impedance. But while writing the KVL, we need to careful about the dots present here. So in circuit 1, the loop 1 current is entering at dotted terminal. Here in circuit 2, the current is leaving. I2 is leaving from dotted terminal. In that case, if one current is entering at dotted terminal, one current is leaving from the dotted terminal. In that case, we are considering the term M as a negative. So that's why I am taking minus J3I2. J3I is a mutual inductance. So I2 I am considering because of it is a voltage. J3I2 is a mutual voltage. It is negative because one current is entering at a dotted terminal, one current is leaving from the dotted terminal of a second circuit. So by simplifying this one, Ji1 minus J3I2 is equals this one. Next, I am considering loop 2. I am applying KVL as usual. So here also minus J3I1 plus 12 plus 6Ji2. Here also I am considering mutual voltage. mutual voltage because of current I1. That's why I am considering negative. Why it is negative? Because one current is entering at a dotted terminal and one current is leaving from the dotted terminal. That's why I am considering a mutual voltage of minus sign. So by simplifying, the I1 is equals to 12 plus J6 I2 by J3. So we can simplify this, further simplify 2 minus J4 by I2. So this is the equation 1 we are getting from circuit 1. Equation 2 we are getting from circuit 2. So by substituting equation 1 and equation 2. So I am substituting equation 1 in equation 2. So we are getting J I2 plus 4 minus J I3 into I2 is equals 4 minus J I2 into L2. So I2 is equals to 12 by minus J. So by simplification we are getting this one. And by substituting current I2 in equation 2. So this current I am substituting in equation 2. Finally we are getting 13.01 at an angle of minus 49.39 degrees. So this is a sample calculation of a magnetically coupled circuits by using dot convention. That is nothing but analyzing of a circuits. Analysis of a circuit involving mutual inductance. So whenever there is a mutual inductance between two magnetic coils, we need to go for dot convention. According to the dot convention, we are giving a polarity for a mutual induced voltage. So we know that if two coils are there, so we are studied in the previous lectures, if two coils are there exists a mutual inductance between these two coils. So here, because of change in flux in coil 1 produces induced EMF, that we call it as a self-induced EMF, and because of some linkage flux. So this some flux is linking with the second coil. In the second coil is also EMF is induces. That induced voltage we call it as a mutual voltage. So that's why to know the polarity of a mutual voltage, we developed a concept called dot convention. So I hope this is clear for the dots. If dots are there, dots are marking on a coils, magnetically coupled coils, to know the polarity of or whether it is a positive or negative of a mutual voltage. But the mutual inductance is positive. Always it is positive, but the mutual voltage or mutually induced voltage in a magnetically coupled circuit is either positive or negative. So that can be decided by the concept called dot convention. So this is all about dot convention in magnetically coupled circuit. Thank you.